Most standard agent harnesses ship with a strict limitation. They run a single, fixed execution loop. You give the agent a plan, act, and observe cycle, and that structure remains completely static. This animation shows how MemoHarness dismantles that standard architecture. It is a meta-harness. The static loop breaks apart into a 6-dimensional control surface, treated as an editable configuration. It actively learns and rewrites its own harness based on execution experience. This creates a strict division of labor. The language model itself is only responsible for predicting tokens. The harness is what actually manages the environment, dynamically searching across those 6 slots: context, tool, generation, orchestration, memory, and output. But here is the operational paradox. In a production environment, MemoHarness does not actually run its own inner agent. It delegates the direct task execution to an entirely separate external runner called HarborCodex. MemoHarness is a controller of controllers. It is a Python framework built to learn how to harness another harness. Transitioning from writing a static harness to searching for one programmatically introduces highly specific vulnerabilities. To understand where this architecture degrades, we have to trace the exact data pathway through the system. Our trace begins at the CLI entry point, passing the data payload into the HarborTrainingLoop. This outer loop manages the search. Its structural boundary is absolute, governed purely by a hard-coded iteration count, typically 20. Unlike standard machine learning, this loop has no convergence guard. Because there is no mechanism to detect a plateau in performance, the system is forced to execute every single iteration. Relying strictly on a hard iteration count turns the outer loop into a brute force compute budget burn. It continues expending resources long after the harness has stopped actually improving. For each iteration, the agent executes inside a Daytona cloud sandbox, isolating its actions from the host machine. Inside, the React loop operates under an extreme mathematical bound. Its turn limit is set to _max turns equal to sys.maxsize. That is the maximum integer value supported by Python. Practically, this means the agent lacks a turn cap. It is functionally unbounded, terminating only if the model voluntarily stops emitting tool calls. The agent is given a single tool to interact with its environment, an unrestricted shell tool called run command. There is no allow list to gate which specific commands the model can execute. Furthermore, the system is instructed not to retry timed-out provider calls. The configuration variable _retriable timeout exception types is left as an empty set. If the model gets stuck in an infinite loop, constantly emitting commands or hanging on a provider timeout, the only failsafe is a hard shard wall clock kill. The host infrastructure simply peps the power to the entire run. Removing turn caps and disabling timeout retries shifts all execution safety burdens away from the agent's internal logic, relying entirely on blunt infrastructure limits. Instead of checking its work in the loop, MemoHarness patches the trial layer, ensuring results are graded only after the agent completely stops. Success is simplified. A parser reads result.json to assign a binary pass or fail, strictly driven by a reward threshold of 0.5. The evaluation relies on capability endpoints, like terminal bench or livecode bench. There is no behavioral regression suite to track if the agent is acquiring destructive habits while solving the task. Discovering failure only after the compute has been spent wastes entire execution trials. It also provides an inherently weak optimization signal for the harness, giving the system very little granular feedback to improve the D6 output dimension. Verified trial data must be stored to inform the next iteration. It is routed here, to the dual-layer experience bank. The top layer is ET, storing the episodic per-case execution logs exactly as they occurred in the sandbox. The bottom layer is GT. On a regular cadence, a distiller evaluates the episodic logs and extracts semantic global patterns, stripping away the noise. But the architecture contains a critical flaw. The bank is strictly append only. It has zero eviction logic and no time to live, or TTL, policies. Data enters, but it never expires. When the frozen harness needs to adapt to a new test case, it queries this bank, using feature-matched slices to retrieve relevant past experiences. Because nothing is ever deleted, retrieval algorithms inevitably pull from thousands of obsolete iterations. Without a TTL policy, the system generates zombie memory. Stale execution entries resurface during evaluation, actively degrading the quality of the learned harness over long training runs. The retrieved memory data enters the final active stage of the loop, the metacontroller. The controller triggers Decide Next Harness, using a language model to ingest experience data and rewrite the 6 configuration parameters for the next iteration. To prevent the controller from degrading the system, a canary acts as a gatekeeper. It explicitly blocks any harness updates that regress the reward metric beyond a tolerance. However, the security context of this operation reveals an asymmetry. While the inner agent executes inside an isolated Daytona sandbox, this metacontroller runs entirely unsandboxed on the host machine. To allow the system to operate autonomously, the controller hardcodes a specific CLI bypass. It explicitly forces the flag -- dangerously bypass approvals and sandbox by default. The repository includes a file named policy.json that appears to dictate security rules. In reality, it acts purely as prompt configuration context. Nothing in the codebase actually enforces the rules written inside it. The pursuit of an autonomously self-writing harness forces the architecture to deliberately dismantle the exact approval and sandbox safeguards required for secure execution on a host machine. MemoHarness is a search parameter matrix designed to harness external runners like codecs. Tracing its execution path reveals 3 core structural trade-offs engineers must address when building a production meta-harness. First is loop asymmetry. Combining an outer search loop that lacks early stopping with an inner react loop that lacks turn caps creates an architecture highly susceptible to infinite loops and massive compute waste. Second is post-hoc constraints. Grading an agent only after execution completes provides poor optimization data, and relying on default security bypasses to achieve autonomy exposes the host machine to the metacontroller. Third is state management. Operating an append-only memory bank without strict eviction policies inevitably leads to state degradation, as obsolete patterns poison future retrieval. Programmatic harness optimization is powerful, but it requires highly specific guardrails to remain stable over thousands of iterations. True agent autonomy demands that safety bounds, timeout parameters, and memory eviction are built natively into the model's operating environment, rather than stripping them away and relying on brittle host-side workarounds.